Look at this split screen. On the left, we have a pressurized water pipe system, and on the right, a basic electrical wire. They operate on the exact same physical principle. The water pressure pushing through the pipe is your voltage. The restriction, like a valve narrowing the pipe, is your resistance. And the actual amount of water flowing through is your electrical current. Let's translate that flow into numbers using this schematic. We have a 12-volt source pushing through a 4-ohm resistor. To find current, use the VIR triangle. Covering I shows the formula, voltage divided by resistance. Dividing 12 volts by 4 ohms leaves a flow of 3 amps. Before you touch a physical wire or distribution board, you have to calculate that basic relationship. Every safety protocol, house wiring diagram, and equipment rating in the ITI syllabus relies on accurately predicting how much current a system will draw. A single resistor gives us a clean baseline, but real-world electrical installations rarely look like that. As an electrician, you are constantly stringing multiple loads together on the same line. Here is that same circuit, but now we've added a second 2-ohm resistor directly in line, or in series, with the original 4-ohm component. In a series configuration, the electrical current has only one path to take. It must force its way through both restrictions, which simply adds them together to create a single 6-ohm total resistance. Going back to our VIR triangle, we take our constant 12 volts and divide it by that heavier 6-ohm total. The current naturally drops down to 2 amps. Stacking components sequentially forces the voltage to work harder to push the same electrons, naturally choking off the total flow of the entire electrical system. That sequential chokehold is exactly why you don't wire a modern house in series. If one light burns out, the circuit breaks entirely. Instead, industrial and residential loads are wired to run independently. Watch how the schematic changes here. We're using the exact same 2 loads, but now the 2-ohm resistor sits on its own independent branch, parallel to the 4-ohm resistor. By opening up a second lane for the current to travel through, the overall resistance of the system actually drops. To calculate exactly how much, we use a fractional formula. 1 over total resistance equals 1 over 4 plus 1 over 2, giving us a sum of 3 over 4. But do not stop here. That 3 over 4 is not your final resistance. To isolate the total resistance, you must invert the fraction. 3 over 4 flips upside down to become 4 over 3, leaving you with 1.33 ohms. Skipping that final inversion is the most common math error made on the NCVT trade practical exams. It guarantees a failed electrical estimation, regardless of how well you know the rest of the formula. Let's test this directly. Take a look at this new parallel circuit schematic. We have a 24-volt battery powering a 6-ohm resistor and a 3-ohm resistor. Pause the video now. Calculate your total resistance, remember the inversion step to avoid the parallel trap, and then apply Ohm's law to find the total current. Solving these on paper trains you to mentally trace fault lines and load balances before you ever open up a live industrial control panel. Let's resolve it. 1 over 6 plus 1 over 3 equals 3 over 6. We flip the fraction to 6 over 3, giving us a clean 2 ohms of total resistance. Finally, we take our 24 volts, divide by that 2 ohms, and we get our final answer, 12 amps. If you reach 12 amps, your calculation skills align directly with first-year electrician standards. This final screen captures everything we've built today. On the left is your primary tool, the VIR triangle. In the middle, the straightforward addition rule for series circuits. And on the right, the parallel formula, complete with a strict reminder to invert your final fraction. Memorize these 3 exact structures. Whether you are running house wiring or sizing protective breakers for a commercial motor, every decision you make relies on calculating these variables correctly.